Hello, my name is Viktor Ulanov. I'd like to tell you about my work in which I investigated properties of hydrodynamic self-oscillation system. Safety of nuclear power plants is a major priority in the future development of nuclear power industry. Water-cooled reactors are widespread and they are still used for future design of nuclear power plants. Overheating of the reactor in case of emergency is one of the main problems of water-cooled nuclear power plants. Fukushima power plant accident in 2011 was caused by overheating of the reactor after the station blackout. Passive safety systems operated by natural forces are intended to use to improve their ability. Passive safety systems do not need external power supply and therefore they are functional in case of station blackout. In spite of all advantages of passive systems, they have some drawbacks. Natural driving forces are quite weak, so the heat transfer of such system is relatively slow. Useful utilization of self-oscillation in a hydrodynamic system is quite rare. The idea of this work is to use controlled self-oscillation of two-phase water and steam coolant in a nuclear power plant passive safety system and other industrial cooling systems. In the first part of the work, we considered a hermetic bottle filled with the water and a tube attached to the hole in the bottle cap. If one turned upside down, the water will start to flow out, periodically letting air in. These are self-oscillations. There are four phases of self-oscillation cycle. Firstly, water fills the tubes. Then water flows out, after water rises through the tube, and finally a bubble arises, enlarges and separates. Then the cycle repeats. To record the experimental data, we performed a video recording at frequency of 120 frames per second and processed it in total software package. At the same time, we recorded dynamic parameters of the system such as rate and pressure using Fourier multi-lab digital sensors. These data were processed by our own program in C++. To understand what's happening and why, we built a mathematical model of the phenomena. For the water flow out phase, we started from the Newton's second law for water in the tube, taking into account the force of pressure, gravity, a reactive force from the Shakespeare equation, and the force of internal friction. We obtained a linear integral differential equation that describes the dynamic of our system. For the phase of lowering and raising the water in the tube, we additionally took into account the force of surface tension and the boundary between the water and air. We got a nonlinear differential equation. For the fourth phase, we proposed an original model of bubble formation and separation at the upper end of the tube. It is based on the theory of free submerged jet. It allows us to calculate the shape and volume of the bubble and thus describe one of the most complicated stages of self-oscillations. The obtained equations were solved numerically by the Runge-Kutta method of force over order. There is a good correspondence between the experimental and model calculation. To study the conditions of self-oscillations, we proposed a method of visualizing the system evolution on diagrams. We observed three fundamentally different types of the system behavior which corresponds to the three zones in the diagram. We noticed that under certain conditions the average flow rate of water during self-oscillations is greater than the rate of direct flow through the same tube. In the second part, we proposed the use of self-oscillations to improve the passive safety system performance of nuclear power plants or other industrial cooling systems. We used method and mathematical model derived for the simple system for a more complicated modeling system. We constructed a model installation which simulates an emergency cooling system for a nuclear reactor. It consists of two hermetic tanks connected by a short and a long tubes. The flask used as a lower tank gets the heat from the oil heater which regulated power up to 40 kW. It corresponds to the reactor core in boiling water reactor or heat exchanger or a pressurized water reactor. The heater makes the liquid in the tank to boil. The upper tank contains a coil through which cold water flows. It corresponds to the cooling system of a nuclear power plant. To get a consistent description of system, a mathematical model was built. As an example, let us show the stage of fluid flow down through the tube. The constructed thermodynamic part of the mathematical model, the following relations were used. The hydrodynamic part considers the liquid and the vapor flow through the tubes. As an example of some results, the numerical simulation and experimental data you could see on this slide. Self-oscillation mode makes much higher heat and energy output possible under the critical pressure. It might be seen on this plot. As in the simple case, we propose to use diagrams to illustrate the total picture of the system behavior. The main results of our work may be formulated as follows. The experimental data and the mathematical model shows that the self-oscillation mode provides more efficient heat transfer than the direct natural circulation. In the case of a reactor, an extensive heat flux from the heater will cause self-oscillations which will lead to more efficient heat transfer between the heater and the cooler. In this way, the critical pressure for destruction of the reactor will not be reached, so an accident will be prevented. Obviously, to be used in real systems, this technology should be deeply studied with full-scale industrial prototype.